Okay, so this is physics notes. This is the boring intro stuff where we talk about what physics is, but we're also going to talk about some scientific method stuff, which is a little bit cooler, and hopefully is an angle that you haven't heard before. So physics is, and I was a biologist in college with a minor in chemistry, and I hated physics. Ironic, I know, that I now teach it. But I remember physics majors being really snotty about how we've got the science you can do stuff with. Whatever. Physics really is the study of the physical movement and interaction of the world. We're mostly talking at the macro level here, though we will talk about some of the subatomic physics that goes on. It's how things interact. We're talking about forces in motion. We're talking about light and waves. We're talking about physical interactions in the world. There are, 7? I can't count out loud fast. 7 areas of physics, that your book breaks down. And I don't know that there are any more. I think this is just the 7 basic areas of physics. Of these, I can tell you that we're only going to do 3 of them. And we will spend most of our year on mechanics. And mechanics, if you think about like a mechanic, somebody who works on cars, mechanics is how things physically interact. So this is your motion and your forces and your acceleration and velocity and work done. All that stuff, physical interaction. It is sometimes terribly confused with quantum mechanics, which it ain't. We'll talk about what quantum mechanics is in a second. So we do mechanics, and that's kinematics, acceleration, velocity, all that. Forces, which we'll spend a lot of time on, and work, which we'll spend a little bit of time on. I wish we had time to do thermodynamics, because it would be so cool, because I would have you people build solar water heaters, and it would be stinking awesome. Sadly, we barely have enough time to do the stuff that really gets you ready for year 1 of college physics, so I can't throw a water heater project in there. But if I could, let me tell you, it would be awesome. We don't do it. Like I said, we don't have time for that. We have in the past, I used to do some vibrations and wave phenomena and some optics. So the vibrations and wave phenomena you probably had in your physical science class. You should have had some basic stuff about longitudinal waves versus transverse waves, wave speed and wavelength and frequency, that kind of thing. It's pretty easy to pick up. If you go into that first year of college physics and you've never had vibrations and waves in your high school physics, you're probably going to be just fine. You'll figure out how to swim and you probably won't die. The optics is probably a little trickier, and I'd love to go back to getting a little bit of optics in. We used to do some good stuff with lenses and mirrors and figuring out image size, image magnification, image location, using focal length of mirrors. But again, if I had to pick something that you can probably pick up pretty well on your own in college, the optics isn't that hard. The mechanics is a cruel mistress. The other part that we do is electromagnetism. And electromagnetism is the circuits and the Coulomb's law and little charges, little things that are charged and how they're attracted to one another. And that's a lot harder to pick up from zero on your own. So we usually do about 9 weeks of electromagnetism at the end, and I'll have you guys build and solder circuits. We'll play with electrical fields a little bit. We'll do some calculations of field forces and things like that. Because I want you to have at least seen it. I want you to not be completely taken by surprise. Sadly, these last 2. Oh, these are the sexy parts of physics. These are the parts that make you interesting at parties. These are the parts that make people go, really? Wow. Tell me more. Nobody's ever going to ask you to tell them more about mechanics. I'm sorry. So relativity is the Einstein stuff. Einstein came up with a theory of general relativity in 1905. His miraculous year, the annum miraculum, something in Latin, I don't know. His Amazing Year, he's working as a patent clerk, and he just like shoots off these 3 articles that change the whole world. So relativity is all this stuff about space-time and how it's curved, and we can talk about gravity wells, which I should show you the cartoon about gravity wells at some point. It's awesome. You know, space and time are a rubber sheet, and we're just all laying in the dips. Really? Ew. Yeah. It's cool. Relativity relates how all this big stuff works the way it does. Now there's a problem. You knew there was going to be a problem. Part of the sort of gold standard in science is that it's universal. So scientific principles work the same way here as they do in Topeka, Kansas. They work the same way here as they do on Mars. They work the same way here as they do, we assume, in all parts of the multiverse. Because you know the math points to 11 dimensions and multiple verses, right? I thought you knew that. Yeah, some of them are apparently coiled up inside one another like little wires. It's very weird stuff. See, that's the sexy part of physics that we don't get to talk about. But it will make you really popular at parties if you go read Brian Greene's book, Elegant Universe. I highly recommend it. Anyway, relativity is how that stuff works at the big level. And in science, we very firmly believe that the same principles and actions have the same effect here and there, and they did 1,000,000 years in the past, and they will 1,000,000 years in the future. There's just one little problem. It breaks down when we get to the subatomic level. Crap. Stuff doesn't seem, there seem to be 2 sets of rules at play. That's a problem, because in science, we can't figure stuff out if there are multiple sets of rules. You got one set of rules, you can take that set of rules and you can look at phenomena and you can interpret them in the light of that set of rules, because those rules work the same way, the same time, the same everywhere. If there are 2 sets of rules, you suddenly have to ask which set of rules we're playing by. It's like showing up at the football game and being told you can't use your hands. That's a different football. So we have to know what the rules are. Quantum mechanics governs the mechanics at that subatomic level. It is different than mechanics. Mechanics is how things move and interact at the macro level that we can see. It's why you are so attractive to the earth. So attractive to the earth. You know how to get more attractive to the earth? Eat more cookies. After Christmas, I am a good 5 pounds more attractive than I am before Christmas, let me tell you. That's mechanics. Quantum mechanics, the interactions of subatomic particles are different. Relativity really starts to try to reconcile those. They haven't figured out the unified field theory. The idea being that it might look like there are 2 sets of rules, but really there's one overarching set of rules that connects those that we don't understand yet. Again, we don't do that. Don't mix up quantum mechanics and regular mechanics. Quantum's more exciting. If you studied all that subatomic particle stuff in chemistry, which some of you did, those are quantum mechanic idea. The quantum model of the atom flows from quantum mechanics. Okay, so we got these areas of physics. Like I said, relativity tries to connect them, but it's not doing so well. We're going to talk a little bit more about Brian Greene. He is my favorite living physicist. I have a whole slew of favorite dead physicists, but he's my favorite living physicist. What a shame. You can look him up yourself. So you don't have to write down that stuff if you don't want to, because what we're going to talk about is the more important part. We're going to talk about Brian Greene when we talk about scientific methods. And note that I say methods, and I will give you my absolute pet peeve. This is where I should have a queued up version of the Scientific Method song from whatever cartoon that was. The scientific method, yeah. You guys, I mean, I guess they have to do this. I hate middle school for many reasons, but they do the whole step 1 of the scientific method, step 2 of the scientific method, step 3 of the. It's not a cookbook. It's not a recipe. It's not a stepwise, set of steps. It's a way of thinking. It always includes careful observation. Even if you are not going into a science field, being more scientific in your movement through the world helps you. Being a good observer can keep you from getting killed. Observations in science, and I like to think in life, should be objective. They should be factual. You can only write down, you can only record information that you got directly from your senses. Once you move past what you're directly observing with your senses, you're interpreting. You're intuiting, you're interpreting, you're extrapolating from the observable data. And we do that. That's good. It's not a bad skill, but you have to be careful about where that line is. So science is just seeking to explain the world, and we explain it through hypotheses, and we test them. So, my little pet mastodon killer hypothesis, of which I discussed earlier, not necessarily testable, so it's not really a hypothesis. How many of you would say that there's a difference between the word theory and the word hypothesis? Oh, thank God. Okay, good. We don't have to do that. I have been known to say to my almost 7-year-old, don't misuse the word theory, that's a hypothesis. I'm a pain in the tuchus. But hypotheses are working explanations of how something functions. It's not a theory, it is a working explanation. It's a testable working explanation. It's the best we know at the moment. Brian Greene is a physicist who works on what is called string theory. So string theory is a theory of the universe that posits, and oh Lord, if you want, like I said, if you want to fill your head full of stuff that will make you very interesting to a certain subset of the population, smart people of whatever you're interested in will think you're really cool if you can get through the PBS special Elegant Universe with Brian Greene. He does a really good job explaining string theory. And there are strings, and there are membranes, and there are 11 dimensions, and there are things curled up inside one another, and things don't toe. Woo! It's great. You can spend a good snowstorm watching that this winter. Sadly, we don't have time for it in class. Brian Greene talks about the fact he's been working on string theory for 30 years. I saw him speak at YSU 15 years ago. They brought him in for a speaker series, and I was like, yeah, I'm going. He said, I've been working on this for 30 years, and every day I get up and I go to work and I try to break it. Really? Because that's what we do in science. We don't prove anything. We continually attempt to disprove that which we believe most strongly. It's a pretty powerful thing if you really let that sink in. So everything has to be tested. Well, but if that's true, then when I do this, that shouldn't happen. Oh, okay, it didn't happen. Well, this is still supported. So it's this constant process. We interpret and evaluate data, we conclude, and we discuss like crazy. You want to think about going into education, you want to think about going into psychology, you want to think about going into engineering, you want to think about going into pharmaceuticals, you want to think about going into anything. Read the latest research. Whatever your thing is, read the research. You want to go into wildlife management? Read the research. Science Daily is a great way to start your day, every single day. They've got little encapsulated summaries of research articles, population ecology of wombats, learning and the juvenile brain, how brains change when they learn, new materials testing stuff. Constant discussion so that other scientists continue to try to break your stuff. Now, the thing that is used most often in science to arrange data to help sort of put it together in some way that makes sense. Well, okay. We have data. We collect data. We organize data. And in terms of experimental design, we very often use models to arrange that data in some way that it can be discussed, in some way that it can possibly sometimes be tested. So models, which we're going to talk about first, are not, who here has built a model, like car, airplane, space shuttle? I built a space shuttle in 4th grade. They were kind of a big deal back then. They're kind of dull now, but it was really cool. So that's a physical model, and they're useful. If you have ever seen, what was the terrifying series on Netflix, Haunting of Hill House? And they showed the little architectural model of the house at the beginning and end of every episode. Physical models are really useful because it shows you if a beam is in a place where it's going to hit a window. Oh, that beam ends in a doorway. That doesn't work. The power plant at Beaver Valley, my dad worked there for years, and when I was a kid, they still had the model. And I think at the time, this was in the 80s, they would say it was $2 million worth of plastic. And it was displayed on a floor in the emergency response building, and when you took a tour, it would walk you through the model. They don't do it anymore. Apparently, it's like in a room somewhere on a shelf. Well, a bunch of shelves, because it was an entire room, like 3 times the size of this room, and it showed the location and color coding of every pipe, every valve, every ladder in the entire plant. They spent $2 million to build a scale model of that plant before they poured the first bit of concrete. Because it's cheaper to spend $2 million on all that plastic than to get from building from the blueprints and realize that in 2 dimensions that works, but in 3 dimensions these 2 things are at the same place. So they build a model. That's a physical model. Those actually are the kind that we use the least. The globe is a physical model of the Earth. What's very commonly used in physics are mathematical models, and these are also used a lot in things like climatology, uses mathematical models. There was a guy, he's a climate scientist, and I remember reading his book years ago, and he talked about an undergraduate coming up to him and going, Dr. whoever, Dr. Jones, can you take me to see the climate model? It's a series of calculations running inside a computer. There's no physical model. And it's calculations that you put in data, you input data. The data goes into the mathematical model, and what the mathematical model can spit out is a series of projections. So for instance, with the climate models that we have currently, how do you test that? How do you test to see if you've got all the factors? Well, how about if you go back 100 years, and for every year of recorded climate data, you input that to the model, and you see how closely the projection matches what actually happened. And that's what they do, is they'll go back in and put, and I think with the atmospheric composition, because of ice cores from the Arctic, they go back a couple thousand years. So you can put in a couple thousand years old data into the model and see if the projections match what actually happened. It's a good way to test your model. Verbal models are just descriptions of things. And that can be describing how an object moves, how something works on an object. Visual models are things like maps, charts, graphs, where you're organizing data in some way that gives a visual relationship. Now, all of those models are useful for illustrating a hypothesis. We think the climate works this way. We've put together a series of mathematical models which illustrate our hypothesis, and therefore mathematical models are useful for testing. Physical models can be useful for testing. We know that these 2 objects at this level interact this way. We're going to do a microscale physical model and see if they interact that way. Useful for testing. Verbal models, visual models, there are things you can't make a model of other than verbally. And thought experiments become the province of things that can't easily have physical or mathematical models made of them. Einstein was great at thought experiments. And we're gonna watch a brief video on thought experiments. Schrodinger was another one who did some pretty cool thought experiments. So I'll leave that to the video. Controlled experiments are something you should all be familiar with. These are the classics where you have a control group, you have an experimental group. You know the joke about the biologist who had twins, right? What did the biologist say when she was told she had twins? Oh, good, a control. How would you be able to resist? Like, I'm going to feed you nothing but carrots for a week, and I'm going to feed you a normal diet. We'll see what happens. Anyway, we're gonna break and go watch 2 videos. Did I talk about the plan? I didn't. Okay. If you would be so kind as to open up your classroom, we're going to pause the notes here, talk about the plan, and then go to the video links in the plan.